Welcome back. A few videos ago, we defined linear combination and spans in Rn. In this video, we'll be defining them for general vector spaces. It's going to look exactly the same, except that the v1, vk are not going to be vectors, so you're not going to find these arrows. They're just going to be random elements of some vector space. All right, so let's get to it. In this video, we'll look at section 1.3.2. We'll define linear combinations and spans in a general vector space. So our goal is to generalize the notion. I'll correct it for the notes. The notion of linear combination and span to any vector space V. We define a linear combination and a span in a general vector space in a similar way that we did in Rn. All right, so here it goes. If I have S, which is a subset of a vector space V, so V1, V2, Vn, a linear combination of S is any sum of the form A1, V1, A2, V2, plus AN, Vn, where A1 through AN are real numbers. We then call W a linear combination of the set S. Now, if we want to look at the span of S, then we take all the linear combinations and put them together. And so span of S is the set of all A1, V1, A2, V2. So everything that you can write as a linear combination, you put in the span. So A1, AN are any real numbers. Something interesting about general vector spaces is that you can actually need, in some cases, infinitely many elements to span your set. So we will, in a few places, use infinite subsets of V as generators. All right, in that case, if S is infinite, a linear combination of S is only allowed to use a finite number of elements of S. In vector space, as is, we're not able to add infinitely many things. We're not able to do series. We're not able to add without stopping. And so that means that when we do a linear combination, it's going to be a finite sum. W is A1, V1, A1, V1 plus A2, V2 plus AN, Vn. And then I'm going to take n to be in a real number, a natural number, so an integer. So I'm picking an integer, and that's going to determine the number of elements. A1 through AN are in R, and V1 through Vn are elements of the vector space. All right, so I'm not using every single element of S when I write this. I just pick a certain number of them, and that's it. All right, similarly, each element of span of S would be built using only a finite number of elements, but these finitely many elements would change from one W to another. So for each linear combination, we're only allowed to use finitely many elements of S, but as we go through every single linear combination, we are allowed to use different ones, and so in the end, we could have used all of the elements of S. All right, so let's stop here for this video. In the next video, we'll be doing an example over matrices of how to do spans and linear combinations there.